Hello, and welcome to the third Geocast for gaming. My name is Dino Boselli, and I'm an engineer on the Google Maps platform gaming services team. The objective for this series is to create a simple mobile game that uses Maps gaming services to create an interesting gameplay. In the first and second videos of the series, we focus on the setup of both game client and game server, with an emphasis on the integrations with Maps SDK for Unity and Playable Locations API. In this third video, we'll illustrate the game client-server integration with two specific examples. First, we'll detail how the game loads and processes spawn locations, and then we'll look at the lifecycle of a game location by reviewing the battle flow. With that in mind, let's get started. Important: the client and server code for this game are available on GitHub at the following URL. Feel free to follow along. Loading and processing game locations in our demo is a multiple steps process. It starts by requesting the world data around our avatar's position. The server uses that information to return all associated game locations, either by extracting them from the current cache or by creating new ones from Playable Locations API. Then, the server response is processed and rendered by the Unity client. Let's look at some of these steps into detail. First, we need to prepare the request parameters. The avatar's current position is used along a max distance to generate a lat-long rectangle identified by its northeast and southwest corners. Conversions between the Unity Cartesian world space and the Maps SDK lat-long coordinate system are done with the use of two helper functions, from lat-long to vector3 and from vector3 to lat-long. Then the client requests the world data by passing the newly created lat-long rectangle parameter along with a unique user ID. That request triggers the server endpoint associated with the battle rest resource, which itself relies on the world service to get all game locations. There's plenty going on with the handling of spawn locations. In a nutshell, the server gets all playable locations for the given map region and loads the current world data cache from Firestore. If the world doesn't exist yet, it is created from each playable location loaded for the selected region. Otherwise, the server computes a differential of the two datasets and performs some housekeeping before sending the response back. Note that in the second video of the series, we provided some references for getting started with Firestore. We kept the response logic simple. The server parses the response time property and compares it to the current UTC time. Note that all times are in ISO 8601 format so that they can be parsed easily on both C# client and Java server. Back to the client, as soon as the response is received, the local cache of game objects associated with spawn locations is updated by performing a differential between the old and new datasets. You'll notice that both client and server perform similar housekeeping operations. Here is how it looks in the Unity editor. Each spawn location is instantiated from prefabs that have specific location controller scripts attached. By design, the name of each location game object represents the unique location ID, and in this demo, we've decided to use the name property returned by Playable Locations API. Location IDs are initially set in the server code when creating new spawn locations. Et voilà! In our second example, we'll review the battle flow vertical. A battle starts when the player interacts with a minion or a tower location. When it happens, the client does a preemptive check on the location status. If the location is respawning or unlock conditions are met, immediate feedback is provided. Now, if everything is clear, the client sends a request to the server for battle details. Upon receiving the request, the server performs some housekeeping before sending back battle data to the client. Let's review some of the housekeeping done on game locations prior to generating battle details. The server loads the location details, which indicate the nature of the opponent and their stats. Depending on the target, the server performs different checks, such as reviewing the response status or evaluating the location prerequisites. In some cases, it updates the player's inventory if game resources are consumed. When the call to the Battle REST API returns, the game displays the battle screen with the information provided for that location, in this case, a minion battle. The choreography of the battle is entirely handled by the client. To keep things simple, this game demo doesn't have any cheat detection code. It relies on the client for the battle outcome. In a production environment, the server will probably run its own battle validation logic. So, the battle is over. A query is sent to the server to generate the outcome of the encounter. It updates the location status in the process. In our case, the minion disappears from the map until respawn time, 15 minutes from the battle end time. Rewards and acknowledgement for this battle are sent back to the game client. With this information, the client displays either a victory or defeat screen, which concludes the battle flow. To recap, in this video we've looked at the integration between the demo game client and game server with a special focus on spawn locations. We've also looked at the battle flow to illustrate the life cycle of a game location. In the next video, we'll add GPS support to our game so that it uses the world around us when running on a device. We'll deploy the game client on mobile and the game server on Google Cloud App Engine. To learn more about Google Maps platform, check out the Getting Started video and the documentation, both linked below. Thank you and happy coding!